They're energy.
So that doesn't matter, huh?
So I put them right here. No, I didn't think I'd have enough room. So I was going to do those first and then the energy ones.
You make it sound like you make it 1 or 2 steps.
Yeah. All right, well, it's start time. Welcome back. I hope you got your test in the original manner. I like to place them out here, save a lot of time because we always have a lot to do here. So hopefully you got your test. If not, come up and get it. They're in alphabetical order there, and they've got your, in the 5 different piles, and they've got the numbers there. Let's take a first look at the numbers. Here is the average of the test, 73. Obviously, you don't need me to tell you that obviously the second test is a much harder set of materials than the first one. And so as we compare and contrast, here's the first one, here's the second one. And pretty typical numbers too. Although maybe our first one was atypically high. And so maybe it looks like the second one is a little bit low, but a typical average. I tried to write the test as 4 straightforward problems, ones we did in class, and then a hard 5th one, although maybe number 3 turned out to be the hardest one for this test. We'll see here. That certainly wasn't the intent. Number 5 was, and number 5 was definitely a hard problem for people, but it turns out number 3 was a pretty challenging one for people also. So we'll look at that. And so that's what I want to do here at the beginning, is take a few moments and kind of write it out and see what you might have missed. There was only a couple 100%, so all of you missed a little something here or there, or maybe a lot of something here or there. And then that's what I want to write out. And so it's a good time to go through that. It also is a good time to illustrate what I said jokingly, but was also serious about is, do you want the answer? Here's chapters 4 and 5, or excuse me, 5 and 6 right here. It's Newton's second law. And so as you look at the test, you'll see 1, 2, and 3 are Newton's law. You write out the equation, solve the equation. Whereas 4 and 5 are energy ones, although 5, which was designed to be, like I said, the hard one, and the one that was designed to give you a lot of troubles, although, like I said, it's probably more debatable that number 3 gave people more problems than number 5. But either one of those gave people a lot of problems. But here's a good chance to get out your calculator and see, okay, how are you doing so far? Where are you? And remember this, particularly after a tough test like this, students tend to get discouraged, and I don't want you to get discouraged. Go through your numbers, go through your calculation. Remember this, that 75% of your final grade is on your tests. And it's not just this test, it's all the tests. And 25% is the homeworks in lab. And with a few exceptions, most of you have done all your homeworks and labs here. Yeah. Is it your final what?
Final grade or final test? What's the percent on that one?
The final is 25%. And your 3 tests are 50%. Okay. Which means about each test is 16%, 16 2/3. Okay. And so if this helps, or if you did well, great, keep it up. If you didn't do so well, that's recoverable also. I've done these numbers for years and years, and basically it comes down to this. You can bomb one test and still get the grade of your choice. You just have to get that grade on the rest of the tests in the final exam. So let's say you really bomb this one, but you still want that A or that B. Well, fine. Get that A or that B on the next test, or that A and the B in the final, and that's what you'll get in class. So you got a chance to blow one, and that's you know, if you didn't blow this one, I suppose you have a chance to blow another one. Hopefully you never will blow a test here. But anyways, back to these calculations. Get out your calculator and see how you're doing here. Put in the average of your first two tests. And so right now the class average on the first two tests is 80%. And so if you break it down this way and realize that, okay, I'm going to do all the homeworks and labs, and I'm going to take the test. If your test scores are greater than 86%, you end up getting greater than 90%, which is that A. And so to get an A, you got to be greater than 90%, which means your test scores have to be above 86%. If we go down to the B, same thing. Your test scores on average need to be above 73% in order for your whole average to be greater than 80%. Which right now the average of the two tests of the class here is 80%. So the average of the class is very much in a strong B territory. You can see the C and the D cutoff also. And so I'll say it again. Take this test, take your last test, put it together, figure out what your average is right now, and that might give you a good indication of what your grade is right now. And so like I said, if the average of your first two tests is 73, then you just made that B cutoff. That would be your grade. And that's how I would kind of predict what would happen. Of course, that's assuming the idea of this formula is whatever you have an average now, if you continued with that same average for the next test and the final exam, that would be your grade. Obviously, you could score higher or lower since we haven't even done half the points in the class yet. So I know we're more than halfway through. In fact, we only got, what, 5 weeks left? 6 weeks, I think, counting finals week. So it's not much time left, but there's a lot of points left because that's where most of the points are in the next test and in the final exam. Question, yeah?
Do you know how many points total we've done in the labs and homework yet?
Total?
Yeah.
No, I don't. I'm not worried about total. The percentage of the homework is 10%. The percentage of the labs is 15%. Together, that's 25%. That's where these numbers came from. I assume you do all the homeworks in the lab. So if I set this equal to 90, set that to 100%, solve for that one, I get my 86%. That's how I solve for that. Okay? So like I said, everybody's different. Obviously, there's a number of you above 86% on the average of your first two, and obviously there's a bunch in between here and in between here. I haven't looked. I don't think anybody's in that category, and hopefully that won't happen, but it can. So, like I said, look at that, and wanted to average. And wanted to emphasize, don't forget to include in your test scores, not only this test, but last test, and don't forget to include your homeworks and labs when calculating your final grade. Students often forget that, especially after a tough test like this, and they're like, ooh, you know, I'm not doing so well. But I suspect you probably are doing a lot better than this test did because of the first test and because of the labs and the homework. Well, let's look at them in case there's any uncertainty you still have about the answers on these. Let me write them out and solve them. And I'll use this as a time to emphasize, and I've just written numbers, 3, 2, and 1 right here. Hopefully you see that same idea that, what is physics? Physics is about a few fundamental, powerful ideas that explain a universal phenomenon. So this is that one idea. This is the idea of Newton's second law. And hopefully you'll see that in each of the 3 problems. I'll start with number 1 here. Now, number 1 has 2 objects. So you need to do a free body diagram for each object. I'll do the 4 kilogram here. I'll do the 3 kilogram there. The string is pulling on each of them as it wraps around. So there's a T on each of them. Gravity is pulling down with mg. In this case, it's 3. In this case, it's 4. Maybe I should put a 4. There's some frictional force. Does this one have friction? Yeah. there's some frictional force here, and then there's a normal force there. And so hopefully you wrote out the free body diagram for this one as well as this one. This one I'll go ahead and take a tilted axis. Call that the x-axis, call that the y-axis. If I do the y first, I can see that there's a normal force, and then there is a component of the gravitational force, that mg sine of 30 degrees. And so that's this gravitational one at 30 degrees. So that would be equation number 1. Equation number 2 would say write out the forces in the x direction. Well, that would be the tension minus the friction minus the mg sine of 30 degrees, and that would have to equal to ma. And so that would be equation number 2 as you look at each of these. And then this equation here, and to keep my signs the same, as I was doing the x direction, I called up the hill positive, and it doesn't really matter, just normally we call to the right positive. So I'm going to call up the hill positive. We don't even know which way it's going to go, and I guess I should have been careful with my friction here. But since I already did it, and most of you figured out also that it's going to be this one that wins the tug of war, if you will. So it does go up the hill. So that's the positive direction. And then keeping to that, let me call 3g minus t equals to 3a. And I guess I should have called this a 4a there. But that's writing out the equations. And so that's our first 3 steps of any problem. Step 1, you got a good physical picture of what's going on? Step 2, right, draw the free body diagram. Step 3, write out the equation. Step 4, solve the equation. And so now the math kicks in here where I need to solve this. And if I do that, I can solve this for n. There's the normal force. mg cosine theta comes out to be 33.9. So then when I multiply it by the coefficient of friction, 0.25 times 33.9, that gives me a friction of 8.48. So there's the amount of friction. This piece, the amount of gravitational force pulling down the hill, comes out to be a 19.6. And maybe the hardest part of the math is solving this for the tension, which would then be 3g minus 3a, and putting that into here. So putting these two equations together, we get 3g minus 3a for the tension, minus 8.48 for the friction, minus 19.6 for the force of gravity pulling it down the hill, and that has to equal to my 4a. And so when I put in my 3g here, this is a 29, and I know everything but a. Solve for a, and there's the acceleration, 0.188. Okay? And so again, hopefully it fits that pattern. Free body diagram, write out the equations, solve the equations. Yes?
A little small. It's
Oh.
a minus 8.4.
Yeah, maybe I should have not tried to fit all these in such a small space here. Which one?
Just the last one.
This one here?
Yeah, that one.
Okay, so this is taking that free body diagram equation and that one. So it's 3g minus 3a from that one. Then minus 8.48 minus 19.6 equals 4a. Yeah. And so there's where the math kicks in here. And when you solve all this, you got a 7a on one side, and the 29, the 8, and that all comes out to be 1.32. So kind of an intermediate step there. Well, the same thing happens in number 2, except number 2, things are not moving in a straight line, they are going in a circle. So hopefully you see what we did in chapter 5 versus chapter 6. So in chapter 5 we did problems like this where things would go in a straight line. In chapter 6 we started making them go in circles, as well as had air resistance. And then so obviously this one turned out to be a hard one. But it was an exact copy of the race car one we did in class. So hopefully that helped a lot of you. But let me go back to number 2 before I get carried away here. Okay, we'll start off and then again do that free body diagram here. So here's the object. We have tension, and you could call this tension 1 or tension 2 or tension up or tension down, whatever you want. I happen to call them 1 and 2. Many of you called it upper and lower. I thought that was probably more useful, that you could keep track of upper and lower. But there is your step 2. And maybe I should pause with step 1, but I think you know step 1. You studied and looked at it for a long time, and you know it's a little object spinning around there. But the first step then you should have taken after step 1, knowing the physical picture of what's going on, is this one, step 2, the free body diagram. So we've got the tension from the 2 objects, and then of course we got the force of gravity. Now there is a little bit of thought you want to put into this, since the strings all have the same length here in the problem. And of course you got a picture on your test, but since these strings are all the same length and they're separated by the same length, this is equilateral triangle. And as an equilateral triangle, you know the total angle is 60 degrees. Go on by there, get your test. All right, which makes then, of course, those angles 30 degrees. All right, so there's the step 1, the physical picture. There's step 2, draw the free body diagram. Here's step 3, write out the equations. And so maybe I'll just put the coordinate system, maybe I'll even call that the positive direction for now. We don't usually call the left to the positive direction, but just so I don't have to deal with negative numbers, I should add these together. So I will start with, let's look at the sum of the forces in the x direction. So in the x direction, I have T1 cosine of 30 degrees. I have T2 cosine of 30 degrees. And those are the only forces in the x direction. And of course, since it's spinning in a circle, and that is the center of the circle, I have that equal to mv squared over r. And so there's our chapter 6, objects going in a circle. The second equation is to write out the forces in the vertical direction. So this is T1 sine of 30 degrees minus T2 sine of 30 degrees minus mg, and that one equals to 0. It is not accelerating up or down. And the problem gave you the speed, so you know the speed, 7.75. They gave you the mass, 3 1/4. You need to take a little bit of thought to get the radius, since they gave you the length of this string as 1.5. So this is going to be 1.5 cosine of 30 degrees, which comes out to be 1.3. But once you put in those numbers, you have just 2 unknowns, T1 and T2. You got 2 equations, 2 unknowns. Solve the math. So this is cosine of 30 degrees, which is 0.866 T1. This same idea is cosine of 30 degrees, so that is 0.866 T2. And if you put in your mass, your speed, and your radius, it comes out to be roughly 150. So there's your first equation. Your second equation, same idea. Sine of 30 degrees is a half T1. Sine of 30 again is a half. I'll move the mg to the other side, but again, the m is 3 1/4, g is 9.8. That comes out to be about a 31.9 there. So there's your two equations, two unknowns. So now you can solve it by many methods. Probably substitution's the easiest one. Maybe not. Maybe elimination's a little bit better, but nonetheless, eliminate a T1 or a T2. And so after a couple of steps of algebra, I get 118.6 for the force number 1 and 54.9 newtons for the force from number 2 here. Okay. So again, what I wanted to do today is make sure you could fill in any missing steps that you were missing, but also emphasize that again, this was the point right there. Sum of all the forces. Sum of all the forces. Guess what happens in number 3? Sum of all the forces. Write out the equation and solve. And of course, to save a little time today, I'm not actually solving the equation, but I think you can, two unknowns, and solve that. It may take a little while. Same thing here. Got some substitutions here. This is a tough equation to solve. I guess that's why we did it in class. So that one I understand why it could be challenging. Yeah.
I think what threw me off on this one was you gave us like the resistance force, and usually you'd give us like dPa or something, like each component of like the resistive force.
You're talking about number 3?
Oh yeah, yeah. On 3. But and then I saw the b squared. And I thought that was part of the units for some reason.
Oh.
So I don't know. I just thought that was weird.
Yeah, okay. Yeah, I don't know how to answer that other than, yeah, I wish you would have asked me so I could have clarified the question better. So you could understand the question better. I mean, it's hard enough to do the question when you understand the question. It's impossible to do the question if you don't understand the question. Yeah. Yeah, do you have a question?
Is G tension on 2 significant unless because gravity is pulling it down?
Oh yeah, so if we want to take a moment and analyze this and our answer, maybe we should, see if this makes any physical sense. If you're looking in the x direction, you can see that the component of either one of these is pulling it in, and so the two together is what makes it go in a circle. Okay, which I don't think was your question. That was pretty obvious to you. Your question was more along than the y direction. And in the y direction, as we can see, that we have more things pulling down than pulling up. So we've got to have a larger one pulling up to match the ones pulling down here. And so we can kind of even guess from the beginning, if you will, to see if it fits your intuition, that I would expect T2 to be significantly smaller than T1. T1's got to be pulling up in enough to balance these two guys pulling down. Yet at the same time, their components pulling inward have to equal that. So I would expect this one to be under more tension and really contributing more to pulling it in than that guy. I mean, this guy does play a role, but yeah, would not in any way expect those to be equal. Because of the fact that these two pulling down got equal that one pulling up, and so that one to be bigger. Yeah. So it's a good question, and something you should always ask yourself as you're working in the problem when you finish it. You know, does this make sense? Does one bigger than the other make sense, or should they have come out to be the same, or should the top one be bigger, the bottom one should be bigger? I mean, do these numbers make any sense to you? And then what turned out to probably be the hardest one on the test, like I said, it wasn't intended to be that way. It was intended to be a copy of that. I can't remember. We did two. We did an ice skater and a race car coming in, going really fast, and saying that, hey, when something slows down, their speed or their resistance is proportional to the square of their speed. So in this case, this happens to be a baseball in the problem. And so the baseball's going this way. which means then we have a resistive force that way. And the problem says don't worry about the vertical component of the speed of the ball. And maybe I should get this one off the diagram. That almost looks like another force or something. But when you draw that free body diagram, that's what you're asked to do in that second step. And so maybe I should say it again. Step one, got a good physical picture of what's going on. And then I drew that crazy picture of the whole ballpark. A lot of people were asking on this one, and then I was bored while you guys were taking the test. And I kind of regret doing that because I put in the dimensions and people started using the dimensions of the baseball field, and none of that is needed, okay? And so finally, if you remember halfway through the test, I just crossed the whole thing out and said, do not use these distances. That has nothing to do with the test. The information on the test is enough, okay? And in case you missed the gist of the problem, this is the whole problem right here. It is an object going that way. Like I said, in class we did a race car and an ice skater. But in this case, it's a baseball. The object goes that way, and the resistance then is going to be some number, which in class we called a b and a velocity squared. In fact, in class we even went into more detail and started breaking this apart. And I didn't do that on the test. I thought that would be, make it too long and too complicated. So I just gave you that number, and that was what this was supposed to mean. 0, 0, 0, 1, 2, 3, 7, 6, 9, v squared. And that's what you're supposed to get at it. I did put in the units too, and that sounded like that part confused you.
Resistive force equals bv squared, right? And so when you said that r equaled this, I don't know, I thought that it included the v squared or something.
Yeah, so this equals the resistive force, R.
Okay, I see.
Yeah, I know. Like I said, so if they didn't make that as clear, I wish you would have asked me. I know a number of you did, so maybe I should have said something to the whole class. But I put the units in this time because I know that last time I gave this problem that without the units that threw people off. So okay, well I'll put the units in this time. Maybe that will be helpful. Well, as I said, then once you realize the problem here, now we can put in our equation. And so this should mean that ma, there's the mass, there's the acceleration, should equal, and probably the first step is to realize it is opposite in the direction. And so there's the negative. Once you realize that, now you can solve the equation, although remember it is a derivative, and so that was our discussion about how do you solve a problem like this where you have the derivative of velocity and then you have velocity, and we said that was our separation of variables. So go ahead and put your v squared together with your dv and leave your other stuff, although it wouldn't matter where you put it, on that side of the equation. So now we can actually do an integral. And so in this case they said it took 0.45 seconds to go from some initial speed to some final speed. And that was our question. What is our final speed? So this should be negative 0.000769 over the mass 0.45 minus 0 when I integrate that side of the equation. When I integrate this side of the equation, it becomes a negative 1 over final speed minus a negative 1 over initial speed. And so now I can put in my numbers of 0.145 for the mass. And I can put in my initial speed of 40.2 meters per second there. And the only unknown is that final speed of the 36.7 meters per second there. And so that was the intent of this problem. And like I said, and maybe I should explain more since this turned out to be the hard one. And maybe I'll encourage you to go back and look at your notes. Look at the one we did in class, the two we did in class, the race car and the ice skater. I think you'll see exactly the same equation, exactly the same integral, and you can set it in. And don't use any of those constant acceleration equations. Okay, this is not a constant acceleration problem. Okay, it's got a derivative, and then you have to integrate it. And it's probably one of the first problems you've had to do. You know, start with a derivative and then integrate it. Other than in your math class, but your first non-math class. In fact, this is probably your first academic class outside of math that even has calculus in it. I don't think you did calculus in chemistry and biology or computer science. Yeah, I think so. So I know these are kind of can be a tough one because of that. Yeah, taking your math and applying it. Well, then in 4, if that made sense, 4 we kind of shift gears where we get into our conservation of energy. And we got two objects moving. One goes down, one goes up. So make sure you include both objects. Maybe the trickiest part here is the fact that they don't go at the same speeds. It's a 2-to-1 ratio. And I thought actually that was going to be the hard part, but it doesn't look like it. Most of you saw the 2-for-1 ratio right away, and maybe because we did 2 examples of it in class. But I start off here by saying, well, what is the energy that you start with? And maybe I'll put a picture here, but they do give this first one 2.4 meters above the ground. Something maybe to think about is the second one. The second one, they don't say what it is above the ground, but they do say it goes up. So really, it doesn't really matter what it is above the ground. It's going to show up on both sides of the equation and cancel off. And that may not be so obvious at first. And so I told myself this weekend when I was grading these, I said, okay, I want to make sure I say that to the students because I think there's a human tendency to, if you don't know how to do something, you'll just make something up or forget about it altogether. And that's kind of the worst way of doing a physics problem. The best way of doing a physics problem is saying, look, I know it needs to have some energy. Even though if I don't know its height, let me at least write it down for now and carry it through in the problem, because you may not see how it's going to be solved or be eliminated until you start digging into it. And so that's what I would say here. I would say start here and write down M, G, H for the first one. And then write down M, G, H for the second one. And granted, you don't know what it is. Some of you redefine the second one to be 0 there, and that's fine. That works too. But most of you wrote down, a Y, or some of you just left it alone, and that's the mistake. You don't just leave it alone because you don't know it. Something that's hard, it doesn't just go away because you ignore it. It's still there. Okay, and we got to treat it that way. And so I thought that is probably a good thing I should tell you as you get now into some harder problems, is you're not going to know how to handle it completely in the first step. That's fine. Write it in though, and write what you do know, and then continue on down and see what happens later on. You'll probably get some insight on how to solve for this Y. Or maybe the y will cancel off, as in this case, and it goes away. But you may not see that right away. All right, but there's the beginning part. So they start here, they're not in motion, and so we only have gravitational potential energy. Then they move, and the problem says this one comes down, okay, and this other one is hooked to this pulley system, so that when this one goes down and now has 0 potential energy, this one goes up 1.2 meters. In other words, it only goes up half as much. So this one becomes 1.5, 9.8 y plus 1.2. Okay? And so now maybe, again, not knowing the y, it's not until you look at the next step do you realize that, well, wait a minute, that y there is going to have the same number as that y there, and so this whole term here is going to cancel with this whole term when you do the distributive property. And so it goes away. And so like I said, don't ignore it. Look at it and keep it going until you can figure out what to do about those things you don't know about. Yeah?
Are you supposed to just know it's 1.2 by the way pulleys work? It goes up 1.2.
Yeah. This is a part of the, I guess, part of the physical problem is how, if this goes down 1 meter, where'd it get that 1 meter? Well, it got that 1 meter from the string that is now a little taller, and there's a string on each side, so it'd be half as much. Yeah. Or maybe the other option is just remember it from the 2 examples we did in class, and I had a suspicion that was what a number of you did. But better still is to look at the pulleys. We could wrap it around 3 times. I didn't. I did that one time, and I think you guys saw that on the practice test. I think that's what Don gave you on the practice test. But that problem turned out to be just a little too hard for students, so I don't usually wrap them 3 times anymore. I remember that test, what Don has on there, and I said, well, I did it twice in class. If I did it 3 times, the students will see it, right? So I've kind of resorted back to the 2 times. I did it in class, they'll see the 2 times. So, but now I think you would see the 3 times. It just takes a little bit of digestion time for those things to sink in. All right, well, back to this problem then. I guess I haven't finished writing down the whole equation. I did the original potential energies, and now I've done the final potential energies, but now they're moving. So I've got this 1 kilogram object moving at some speed, and I've got the 1.5 kilogram object moving upward at some other speed. And again, it has that same 2-to-1 ratio. So this one here, number 1, goes twice as fast as that one. So number 1 is twice the speed of number 2. Or put another way, the one going up, number 2, has half the speed of number 1. And that's really what we need as we write this out. So this becomes 1 times 9.8 times 2.4. This then becomes 1.5, 9.8, 1.2. This then becomes 1/2 times 1. And if I leave this as speed 1 squared, and then replace speed number 2 with speed number 1 cut in half and then squared, I have one unknown here, and that is speed number 1. So I know that, I know that, I know that, I know that. Well, I don't, except for the V's. In fact, this came out to be 23.52. This comes out to be 17.64. This coefficient comes out to be 1/2. This coefficient, including the factor of 2 there, comes to be a 0.1857, and so the speed is 2.92 meters per second. So there's your conservation of energy. So again, write out the equations and then start to solve it, and sure enough it will work out eventually. And then finally, to the hard one on the test, the one that many of you did tell me. I got through those 4, and then I just sat there for the last hour looking at number 5. And this is the one where you've got to put all the chapters together. We've got the friction from chapter 5. We got the spring from chapter 7. We've got the circular motion from chapter 6. And we got the conservation of energy from chapter 8. I mean, this is, without a doubt, was designed anyways to be the grand finale. It's got something from all 4 chapters that we just did here. And maybe the first place to start with is in a hard physics question, is if this object is going to go up and around this track here, the question just says about sliding, what maximum distance can the block be placed from the track so that the block just makes it to the top without falling off. And so let's just stop right there and ask that physical question. Why would it fall off?
Normal force.
Okay, so gravity's pulling it down, and so in order to stay up, can you just be going 0 speed up there? No, and that was the hint I ended up giving you eventually and saying, look, the speed cannot be 0 up there. You're going to make a loop, you've got to be moving. I mean, I can't just take this little cap in my hand and say, okay, will it stay? It doesn't stay in my hand. But if it is moving, does it stay? Yes. Right? And so there's a certain amount of motion here that will allow it. And that's an important, critical physical question right away. And if you don't see that, you get stuck. And then you don't know what to do, I realize. And so that's what, to me, makes this a hard problem. Seeing that physical one, as well as putting the 4 chapters together here. So this one is with the idea of the free body diagram. The first step here is to take this and go, okay, when this thing is up here, there's a normal force pushing it down and there's an mg pushing it down. And if you add those two together, normal force plus mg, that is going in a circle, so that has to be mv squared over r. Okay? And that's the physical step from, like I said, chapter 6. You need to realize it's got to be moving here. And if it is moving, it has both a normal force and the force of gravity, which is making it turn. But the question goes on to say, how far can you push it back? And I think you begin to see what happens is if you have the object real close when you shoot it, it easily makes it around. I mean, this thing's going so fast that the mg is not enough. The track has to push down with some normal force in order to complete the circle. But as you get further and further and further and further back here, because of the friction, this block, when it gets here, is going to be going slower and slower and slower. And so what is that minimum speed? And the key is right there, that when the normal force goes to 0, the track is no longer pushing on it. It would fall before it got to that point, because to get to that point, the only way it could stay up is if it had like a negative normal force, whatever that means. Maybe if these were magnets instead, and we would be pulling it up here. So there's the key to the first step, to realize that to just make it up to the top. If you launch it real close, it easily makes it around. And as you get further back, it barely makes it, and at some point it just barely makes it. You go a little bit further and it's going to go up here and then fall off. It just doesn't get to the top. And so, like I said, that's, to me, was far harder than this, especially since we saw this in class. And I don't think we did this in class, but I think it was a homework one, wasn't it? No? Going upside down on a loop?
It was a bead.
It was a, yeah, well, the bead was a little different, though.
But it has the same idea as a normal force.
force is going the same.
Yeah, right. It had a lot of the same thing, except the bead, since the wire goes through the bead never actually falls. So in that sense, it was different. But yeah, you're right. It had a normal force in it. Anyways, if you had done this first step here, you can see that you come up with an R radius times G times V squared. And you put in the numbers. And step number 1 here is, what speed do you need? You can't just have 0 speed. This is the smallest speed, 1.85. If it is going faster than that, it will make it around the loop. If it is going slower than that, it won't. It will fall off here. It will fall off prematurely. And so that's the speed you must have. Now, knowing that, like I said, which is information from chapter 6, we can now put the other chapters together and say, okay, so here's my spring. Okay, and I'm going to compress that spring, as they said, 30 centimeters. So as I go to add up my energy, I have my 1/2 K X squared. And so there's our chapter 7. What is the energy stored in a spring? So that's how much energy you have. And then you launch this thing, and it goes from here across to up over the loop. And so when it gets right to here, 1/2 mv squared is some of the energy it has. That's where this is going to come in. So it's got to have kinetic energy. It's also going to have to go uphill. So there's our chapter 8, our conservation of energy. It's gone up the diameter of this circle. It has gone up to here. So this energy has to be enough energy to give it speed, but it also has to be enough energy to give it to its height. And then finally we realize that there's friction along the way, so we're going to have some friction there. And so this is the main equation. But if we put then this into here, and our idea of heat and friction from chapters, I guess it would be 5 and 8, we should have one unknown here. So 1/2 times 450 times 0.3 squared times 1/2, what was the mass of this thing? 0.55, speed 1.85 squared. Its gravitational potential energy is 0.55, 9.82 times 0.35 plus, and then how do you calculate heat? Yeah, force of friction times distance traveled. And it says the force of friction is 7. The distance traveled, well, this is the unknown we are looking for, and then it travels half a circle. So 1/2 of 2 pi r. Okay, and so there's my half a circle. So I know that, I know that, I know that, I know that, I know that. I don't know x. And so we've got a little bit of arithmetic to do, and it comes out to be 1.12 meters. And so there's the height. And some of you did and did not include the 30 centimeters. And to be honest, I didn't mark off for that. I said, you know what? That's just the way they interpreted the question. It's not what I meant, but I could tell from the information that how they included the 30 that, you know, they knew what was going on. It was just a matter of, you know, was the question clear? And I go, well, I'm not going to worry about that 30. So if you want to subtract 30 off of here and say, well, this is where you start, feel free to do that too. So that too was a good number there, and said, okay, well, that's how far back you have to do it to get it started. So good stuff. Tough stuff. And 2 tests out of 4.5 tests. Well, the final counts a little more, so I don't know if you want to call it probably I should just call it 2 tests out of 4 tests. You've taken half your test. But since the final exam is a, counts more, it's the equivalent of a test and a half. So, like I said, if you're just trying to count tests, you're halfway done. If you're trying to count points, you should probably count it as not quite half done. I've done 2 out of 4.5, and so got over half the points still to decide. All right, well, like I said, for better or worse, that one's behind us. Hopefully you learned a little bit in all this. That's really the main idea, is that you are able to do some harder problems today than you were yesterday or a couple weeks ago. And so we've really done quite a bit now. If you think about this semester, I mean, the first test, all it was kinematics. I mean, that's all we had to work with. There was no tough decisions like back here. Is this thing going in a circle or not? Do I use energy or not? I mean, how do you solve that? In fact, some of you back in number 3 were kind of asking that question to yourself. And we're trying to do this in terms of energy. And I think every time you try to do it in terms of energy, you get stuck. Unless, well, you could do it wrong and not realize you got stuck. But if you do it right, you always end up at a point to get stuck. So remember this, if I didn't say it enough last time, is how do I know to use accelerations versus energies? I mean, what usually is the key giveaway? Well, accelerations are usually related to time. And so if something's given in terms of time, you probably want to go down this road of forces and acceleration. And that's what happens in this picture problem. What is its speed after 0.45 seconds? Whereas an energy problem, an energy is force and distance. And so you want to do it in terms of energy when you've got distance is involved here. Okay? And so that would be the approach with that one. And so kind of decide, is this going to be done with Newton's laws, or is this going to be done with work and energy? And like I said, you've done so many now that it makes some tough decisions. And I would probably venture to say that is what makes this semester and next semester and next semester harder, because you've learned so much. And you've got to step back and look at that problem and say, ooh, how do I handle a problem like this? So you've done kinematics, you've done Newton's laws of motion, which included straight motion and circular motion and air resistance. You did energy, and not on this test, but on the next test, you've done momentum now. And now we're going to do rotations. And so you can just imagine the choices you're going to have when we get to this final exam. You're going to make a list and go, there's 5 different things we covered in mechanics here. And you got to look at it and say, is this an equilibrium problem? Is this a kinematics problem? Is this a momentum problem? Is this a rotational problem? And say, okay, what fundamental principle am I going to use? I know it's solved by one of these fundamental ideas, and we did 10 of them. And so how do I, attack it? Well, all right, back to where we left off, and the start and stop of this last one was kind of weird because we put the test off from the spring break here, and so things kind of got mixed together. But now if we can kind of regroup and focus, you remember we've been working here on Chapter 9, and Chapter 9 was on momentum. And so I did a lot of problems for momentum, and I'm going to just ask you, go back and look at what I did last Monday and say, okay, all I did on Monday was example after example after example of things coming together, things colliding, and saying the momentum before equals the momentum after. And then we did some energy issues. There's only one small idea we haven't covered in Chapter 9. So I thought, well, when we're done with the test today, let me mention that last thing in Chapter 9, but really go into rotations. Here's Chapter 10. And so we'll go on to the next chapter here in just a second here. But that last thing that we didn't really take time to talk about was center of mass. And your author throws it here in the second half, and really as a way to prepare you for the next chapter. And so let me use that since I'm ready to start the next chapter. Let's do this. I mean, let's say I have something like this hammer. And we've been working for a long time on this and say, all right, how much potential energy does it have when I lift it up? How about if I lift it up? I mean, you know how to calculate potential energy, right? It's mgy. So if I lift it up, what's y? Because it kind of looks like this part of the hammer only went up that high. But this part of the hammer went way up here. So which y do I use? And you're hopefully already seeing it and hopefully remembering it from 102. This idea of center of mass comes into play when we start thinking about our objects having size. We have not given our objects any size. And I know you felt like you've done some hard problems. But if you stop and think about it, none of your objects even have size yet. Right? I mean, when we take this little object, when we had that, you know, number 5, that little box going around there, we didn't even ask how big is the box, right? And so now we're going to start asking that. We're going to start saying, look, you want to calculate the gravitational potential energy of this. When you lift it up, because the object has size and it can rotate along the way, don't different parts of it go up for different size? I mean, I'll do another one here. If I were to take this hammer and toss it across the room, going back to chapter 4, what path does it take? Yeah, and I bet you can watch this going, is that a parabola? That didn't look like much of a parabola to me. In other words, what we did is point objects. We did not give any object to our size, or any size to our object here. We just tossed it across the room and said, oh, it's going to make a parabola. But the truth is, all objects have size. And this is the first time we do anything that has size. And obviously, you have to give your object size before we can get into the next chapter and make it rotate. If it doesn't have any size, you can't really talk about it rotating. So that's why your author at the end of chapter 9 here says, let's think about objects that have size to them. And once they have size, now we can make them rotate. And so we're going to make things rotate as we get into chapter 10. That's what chapter 10 is all about. And many of you see it already. I don't know if you saw it naturally or you saw it from the Physics 102 here, but there is a little mark here. In this case, it has some red tape on here. If I put my finger right there, we call this the center of mass. And what we mean by that is the effect of all this mass and distance is the same as mass and distance here. Or this one, I think, shows it a little bit better. Light object, heavy object. If you toss it across the room, what part of this object makes a parabola? Or if you lift it up, what part of it do you say is the y? Yeah, it's what we call the center of mass. And so this point here is the center of mass. And I like this one because it illustrates really well, is the center of mass the center of the object? No. So we're not going to be measuring from the center of the object. We measure from a combination of distance and mass. It's what you might call the average of these two. But you might call it a weighted average. Instead of saying the mass of that one and the mass of that one divided by 2, I would say this. What is the center of mass? So X, center of mass. Let me draw this picture here. I've got a big object and I've got a little object. If I were to say that they are separated by a distance of L, and I were to tell you that the little object has mass m and the big object has mass 3 times as much, then when I take this object and I lift it up to calculate its gravitational potential energy, or I toss it across the room and get its parabola, or if I calculate its kinetic energy, it's the kinetic energy, it's the velocity of what point? Do you see how it would spin? And each point would have a different velocity? And all this stuff we've been talking about in the first 8 chapters of this book, we're talking about a point. And so we need a magical point. And that magical point is its center of mass. And so we like to say that even though the object is not a point, there is a magical point called its center of mass. And that center of mass has exactly the same properties. And so that's the key here. In other words, going forward and giving our object size, we now talk about its gravitational potential energy or its kinetic energy or its parabola. We have to talk about a point on that object. What is that point? Center of mass. How do we find it? And that's what this last little part is. This gives us a way to calculate where is that center of mass. It's absolutely crucial. We know that in order to calculate its energy. What's nice about it is that means all those principles that we learned before are still valid. Okay? It's not like we did those 8 chapters and said, oh, we're going to throw that away and give our object size now. That's not what I'm trying to say. What I'm trying to say here is don't forget any of the stuff that you've already learned, because we're going to continue to use it. But when we measure how high the object is, we have to say how high is its center of mass. When we measure how fast is it going, we have to say, well, the center of mass, even though other parts may be moving faster or slower because they're spinning around that center of mass. And so the center of mass becomes the crucial step here, right here. How do we get the center of mass? And what I was saying is this is a weighted average. In other words, if you took the mass of the first one times the position of the first one, the mass of the second one times the position of the second one. And I'll pause right there to say, notice I'm not adding up all the masses and getting its average. Notice I'm not adding up all the positions and getting its average. It's the two together. And so it's mass and position. If you were to add all that up, and you can look at this either way, maybe I'll start here, but all of those added together could represent the whole object, the total mass at some magical point. You'll see it in your book written this way: center of mass is a summation of the first object and the position of that first object, so I equals 1, and then you add it up for the n objects you have, then you divide it by the total mass, and that is the position of its center of mass. Where is its position?
When you say x1, x2, those positions, are they relative to something?
Oh, okay. Now their position then, of course, means I need a coordinate system. And so like we've been doing in the past, I've got to pick a 0 point. Okay? And in this little formula, that hasn't been chosen. So maybe I should ask you, let me do an example. And to do an example, I need to decide, okay, where do you want me to put the origin? It doesn't matter where I put it. Some of you may choose to put the origin here at the bigger one. That's fine. Some of you may choose to put it at the smaller. That's fine. Some of you may choose to put it at the center. That's fine. Some of you may be choosing here, although That's not a very likely case because we don't know where there is. We're trying to calculate where there is. But the point is, you could put it anywhere you want. And for that matter, I could put it down here, although I wouldn't recommend that either. But I would say this. No matter where you put that origin, when you calculate the center of mass, we will all agree it's right here. Now, if you happen to pick this as your origin, you would get a positive number. If you pick this as your origin, you would get a negative number. But we all would agree it's right here. What we don't agree with is how you represent it, positive or negative, because we haven't done the same 0 point. But we all agree where it is. Yeah.
And then additionally, is there a y component?
Yes, yes, good observation. There is a y component here too, and I've avoided that for the moment. That's going to pop up here before we're done in the next few minutes. But yes, we got to do it for x, and we got to do it for y. So let me throw this in here. Let me ask you, all right, where do you guys want me to pick the origin? So I can actually do this example. I want to actually calculate this. Where is the center of mass of this one?
So that the big one.
Shall we do this one? Okay. I think that's the best choice, partly because I just like positive numbers, and it's the biggest one there. All right. So if I pick this to be the origin, as I go to write out this formula, I would say, okay, let's take the mass of the first one, 3m. What's its position? Well, 0. That's where you wanted to pick the origin. You wanted to pick the origin at the position 0 where that big one is. Okay. All the more reason why I like picking that as the origin, because 0 times any number is 0. And I like when zeros show up in the equations. They make my equations easier. So all the more reason that's a good choice. The other one has a mass m and a distance L away, right? In this first example, that's all we have, just two objects, a big one and a little one, and I'm kind of ignoring the weight of the rod in between them. I'm just saying, okay, I'm just using that for connecting them. And then divided by their total mass, which would be 4m. And so I get m over L and 4m. Now, maybe I should have even said, like I was doing a few minutes ago on the test, I'm looking at this m going, ooh, I don't know it. Okay? Well, just write it down. You don't know it. M, maybe it'll cancel off like it did in number 4 there. And sure enough, I don't know what it is. And fortunately enough, it shows up down here, which, again, I don't know what it is, but I do know it cancels off. And so I get 1/4 of an L. And so according to this, it's 1/4 of the length of it, which, again, I don't know what the length is, but I'm not going to worry about the actual number, but visually you can now see that. Here is the whole length. This is about half the length. This is 1/4 of the length. And sure enough, putting a string here or putting your finger here would support it because it's as if all the mass was right there. And so now, if I push on it or I throw it, it's this point that makes a parabola. If I lift it up, the question is, how high did this point go? I don't care that that thing spun around and went higher, right? It's how high did its center of mass go? And so the two objects get incorporated into one, and it's going to make things that are a complicated system of 2 or 3 or 4 or 5 objects reduced down to one little point. So I'm still going to use my conservation of energy. I'm still going to use my parabolic motion. I'm still going to use my 1/2 mv squared. I'm just going to use it for this magical point called its center of mass. Here's one of my favorite ones. Where's the center of mass of this bird? Yeah, it must be at the beak, right? Is that the whole point? And this one will break. I won't toss it across the room here. But if I did, it would spin around its beak, right? It would make a parabola and all the other parts would spin across. If I lifted it up, I would want to know how high did that beak go to calculate its potential energy. If it was moving across the room, I would want to know what's the speed of the beak as it moves across the room, because that's the 1/2 mv squared here. And so maybe now you can see it in the equation here. If you kind of look at this bird, and we call this the x direction, if you will, draw a line here at the beak. And if I draw a line here, you can see that I got a lot of distance back here, right? But very little mass. If you got a chance to look at this after class, this is hollow plastic. Whereas this direction, just past the beak, I don't know if you can see the wingtips. The wingtips are actually just past the beak. And they've got little lead weights in them too. And so we don't have much distance, but we've got a lot of mass. Such that the center of mass comes out to be here, which again, emphasize, it's not the center of the object. And of course, this one is designed purposely to give that illusion of flight there. And so you would look at it, but mathematically it's really nice, showing it's not the center of the object. In fact, the little toy store where we bought it added to it, they've tried to put a little cone, and I think the tapering of the cone is supposed to add to the illusion of being in flight. Although I like the corner of the desk, but I'm not sure which is better there. But I'm always thinking it's going to fall off or something there. Okay, and so this is obviously a very extreme case from that. But for those of you who go into mechanical stuff, mechanical engineering, I mean, that's what we want to know. Where is the center of mass of this engine block? Because I'm going to put this engine block into this frame. And so now I've got this frame of this car, and I've got this engine block. Where's the center of the mass of the two together? Because that's going to tell me the characteristics of this car. How fast is this car going? How much energy? How fast can it go before it tips over and rolls? You know, where is the center of mass of the whole combination of the engine block, the transmission, the frame, and maybe any luggage that I throw in the car here? And so where is that center of mass? And so, like I said, the center of mass becomes a important piece here. Now, let me go one step further, which was your question. I've only done one dimension. What if this is a two-dimensional type of object? What if it has a weight here, and a weight there? Calling this M1, M2, and M3. Right, and so this would have position x1 and y1. This would have position x2 and y2. This would have position x3 and y3. And so that object, if you lifted it up or you tossed it across the room, it needs to have a center of mass. Where would it be, you think? Now, if I'm judging this on size, that kind of looks like that configuration. I would say the center of mass, but this one keeps it down. So maybe the center of mass is about this line. And then in this direction, maybe it's this line. So I'm kind of thinking that's the center of mass. And just a visual guess, I'll do a calculation in a second here, or at least I'll write out a formula for it. I'll look up some numbers and put some numbers here. But again, this is that whole idea of center of mass. The center of mass would be a coordinate system. It would have an x, a y, and for that matter a z. Although, as we've done in the past chapters, we'll do in this chapter, if you could calculate the center of mass x and center of mass of y, it's kind of assumed you can do z. And we don't do too much 3 dimensions until we go on to other semesters and kind of let this sink in for a little bit. But I'm getting at is I would have 2 calculations here. I would have a calculation, what is its center of mass on the x-axis, and what is its center of mass on the y-axis. And I would do them exactly the same way. I've got 3 objects, so it would be m1 x1 plus m2 x2 plus m3 x3, all divided by m1, m2, and m3. And so, same formula, same idea, just take what we call a weighted average. Figure out where is this position. And then likewise here in the y-axis, I would have M1, Y1, M2, Y2, M3, Y3, all over the total mass of M2 and M3. Okay? And so there is a two-dimensional center of mass. Now I say all that because if I go into chapter 9, as we kind of put some closure here, let me give you what I think is one of the harder center of mass one. Well, somewhat hard. 40 is a hard one, a magenta one here that you're going to be asked to do on your homework, so I should address that one. But it's number 37. Number 37 looks like this. It says, in the manufacturing process, we start with a piece of sheet metal that is 30 centimeters on each side. So it takes a piece of sheet metal and says, let's divide it into 10, 20, and then 30 centimeters. 10, 20, and 30 centimeters, putting the origin in the bottom left-hand corner there. Okay, so that's what we start with, and then we cut it. And here they make what I would call simple cuts. They cut along this line there, then along this line there, and then along that line there. And they keep this part. So they throw away the, excuse me, they recycle the rest of the sheet metal here. All right. So we have a part that looks something like this. Now, again, the shape of the part is really not so relevant. Fortunately, they're nice right angle cuts, so that the calculation will be a lot easier than what we're about to see. But starting with the simplest one here, could I find the center of mass of this? Because I'm going to bolt this on, say, the car. And now once I add this to the car, what's the position of the new center of mass, right? And I'm going to end up putting an engine and four wheels and a transmission and a drivetrain and a frame and seats. And by the time I put all that together, I need to know what is the center of mass of the total object. Because that's the object that I need to calculate its kinetic energy, 1/2 mv squared. Right? Its potential energy, mgy. Its parabola, if the car leaves the ground, that's probably not a good example. But you know what? We can figure out this whole center of mass here. So that's where these two come into play. All right, well, here's probably the key to it. Why don't we do this? Why don't I think of those as 6 squares put together? Fair enough? And then hopefully you're seeing it's really kind of the same problem here. Isn't that what I did here? I mean, what I did here is I had 2 objects. Now, each of those objects had size. But did you catch you did something without even asking about? Where was the center of mass of the sphere? Did you say it was right in the center? Yeah, I didn't even ask for you to explain that, but you did that. Now I want to ask, why did you do that? Why did you put the center of mass of the sphere right in its center?
Because it's symmetrical once you
Yeah, it was a symmetrical issue. I mean, it was hopefully so obvious that you didn't even question it. You're like, well, yeah, of course it's the center. You looked at this and you said, look, if you have, you know, mass and an equal amount of mass and position, if these are symmetric, well, then the center position is going to be halfway in between. Fair enough? If I had done equal masses here, wouldn't you have said the center of mass is right in the middle? Okay, so in your mind, maybe without expressing it, you are doing a symmetric calculation. Now I say that because when I chop this into 6 pieces, where is, say, the center of mass of this one? Man, I would put the center of mass right there. Where's the center of mass of this one? Center of mass of this one? This one, and this one. So the reason I cut it into squares is because without really thinking or doing any work, could I know the center of mass of a square? Yeah. And so I've picked a nice symmetric object and put it together. That is the center of mass of the square. In fact, now that you see that, I probably could have saved myself some work and instead of cutting squares, cut less rectangles. And I bet you could even tell me where the center of mass of a rectangle is. Yeah, but I didn't go that road. But I could have had 3 rectangles, and that might have been easier than 6 squares. But the squares, I think, are very easy to see the center of mass. Now that you know the center of mass of the square, and the reason why you're saying it's in the center, and the same reason you did over here, now it fits the logic of if you know the center of mass of the square, put 6 squares together and you can get the center of mass of the whole 6 pieces. And take that piece, put it with another piece to get the center of mass of whatever's been bolted together. And then again and again and again. And so you can keep finding, starting with simple ideas, and get a very complicated idea of what is the center of mass of the space shuttle. You know, as you start putting on engines, computers, life support systems, payload, you know, where is it all? So let's try this one here. Where is the center of mass here? And so if I say X center of mass, I can do a calculation. I need an origin though, right? So where do you want to put the origin? I'm going with bottom left. I mean, that's kind of how the author labeled it from the beginning when he said count this as 10, 20, and 30 centimeters. So let's put the origin bottom left here and keep it there. That's where it was when we started, so I'll leave it there. But if you do that, then let's start looking, and maybe I will start with these bottom ones and then go up. And so the first one may have a square that has mass m, and is at position 5. Right? And then this square has mass m, position 15. And then this square has mass m again, position 25. And then I'll go up to this square, mass m, position 5 in the x direction. So I'm only worried about x right now. And then this one has position 5. Don't all 3 of these have position 5? Can I just put a 3 in front and save myself a little writing? That'd be okay? All right, because I would have an M5 and an M5 again. All right, so I'm just going to put a 3 in front of that because I got 3 of those at position 5. How about this one? Yeah, so that's a 15, so I'm going to go times 2. And then I can divide it by the total mass. The total mass would be 6 times whatever that mass is for one square. And so again, maybe it fits that model again. I don't know what the mass is for the square, and hopefully it's going to go away before I'm all said and done, or I'm going to be able to figure it out. And I can. And so in this case, what does it come out to be? That's a 15m, that's a 30m, that's a 25m. So what is that? 30, 50, 60, 70? So I've got 70m over 6m, 70 over 6, 10,
11.6 repeating.
11,
11 2/3.
okay. 11 and 4, yeah, 2/3, right? Okay. Okay, so 11 and 2/3. Good. And so there's the center of mass in the x direction. Where is it in the y direction? Well, in the y direction, again, let me count them, but it would be okay if I just put these 3 together. Aren't these 3 at position 5? So it's m times 5, but there are 3 of them. The next one is m times 15, but there's only 1 of them at 15. And the other one is m times 25, but there's 2 of them up there. And then I can add up the total masses. There's 6 of them. So that's a 15 and a 15 is a 30. Together with a 50 makes 80m over 6m. And so again, the m's cancel off. 12, are we at 13? 13, and is that a third? 13, 68, yeah, 78 and then 2, okay. So there's my center of mass there. Now if I put that in the chart over here, maybe I'll change colors, but where would that be then for this object? Well, 11 and 2/3 is somewhere along there. And then 13 and a third is somewhere along there. And so there's the center of mass of the object. By the way, is there any mass at that point? No. Is that a requirement? No. All that means is if you were to toss this, it would spin around that point. No different than if I took a loop and I threw it. What does it spin around? Center. Is there any mass at its center? No, but that's the center of mass there. So it doesn't have to have mass there to be part of its center of mass. But that's how I would calculate its potential energy. That's how I would calculate its kinetic energy. That's how I would calculate its parabola.
So is it a vector quantity?
Oh, I guess then you might call it a vector here, yeah, because I've got x and y, so I could say, okay, center of mass vector is 11.66 I hat and 13.33 j hat. Yeah, so there's my position of the center of mass. So calculate them separately or put them together collectively and put an I hat and a j hat on them. Okay. So there's your center of mass. Let's try another one. 43. 43 I like to do because you have one very similar to 43. 43 has a canoe, but you have one. Oh, you know what? It might not be in this edition. Maybe you don't have the turtle one anymore. I think you do. I'm just not sure where it is. But let's try 43 nonetheless here. Look at 43. I like this one because now that we've just spent time trying to show you how to calculate it and along the way kind of explaining why we care about it, this is an excellent one that requires you to understand not just how to calculate the center of mass, but what does the center of mass actually mean? Why are we concerned about the center of mass? And we can use that to our advantage.
What number is it?
Listen to this one. That's 43. So number 43 says this. It says, Romeo, who weighs 77 kilograms, is entertaining Juliet, who weighs 55 kilograms, which every time I read this, I can't help but ask, I don't think she would appreciate somebody telling how much she weighs. But we're going to need that for our calculation. All right. So we got Romeo, who weighs 77 kilograms. We got Juliet, who weighs 55 kilograms. So Romeo is entertaining Juliet by playing his guitar in the rear of their boat, which is at rest in calm water, 2.7 meters away from Juliet, who is in the front of the boat. Let me pause right there. So the boat looks something like this. Maybe this is the back of the boat. This is the front of the boat. According to this, we have, and I'll put a J here for Juliet, and we're told that she is 55 kilograms. Romeo, meanwhile, is 77 kilograms, playing a guitar. There we go. So, oh, man, that's the best it's going to get, I think. All right. Okay. Yeah, it looks more like a violin, huh? All right. But anyway, so there's the two people, and we're told that they are a distance of 2.7 meters away. Let me read it again here, just make sure. Romeo, 77 kilograms, entertains Juliet, 55 kilograms, by playing his guitar from the rear of the boat, which is at rest in calm water, 2.7 meters away from Juliet, who is in the front of the boat. After the serenade, Juliet carefully moves to the rear of the boat, away from the shore. All right, so we must have a shoreline over here somewhere. So here's the water. Here's the shoreline. Okay, and so Juliet is going to move towards Romeo. Okay, move to the rear of the boat, away from the shore. After the serenade, Juliet carefully moves to the rear of the boat, away from the shore, to plant a kiss on Romeo's cheek. How far does the 80-kilogram boat move towards the shore? How do you answer that one? All right, well, the boat's 80 kilograms. All right, got that. How far does the boat even move? Why would you say the boat moves? Make sure that first step is met. Got a good physical picture of what's going on. You can avoid so many wrong directions here. But this truly is a good problem that does not say, calculate center of mass. But it's going to make you figure out you're supposed to do something with the center of mass. So more on that in a second. But does the boat move? Yeah, why? Does the wind blow the boat? No, there's no wind. Does the water current push the boat? No. What makes the boat move? Okay, yeah. It's Juliet. As Juliet pushes herself forward, she pushes on the boat backwards, right? This is that equal and opposite. So the whole idea of getting started is she starts going this way, she pushed on that. Okay? Now, even if she continues to walk at a constant speed across that boat, didn't she already get the boat started? So the boat's heading towards the shore. Is it going to keep heading towards the shore and hit the shore? Juliet has to stop at some point when she gets to Romeo. And what's she going to do? How is she going to stop? So she pushes on the boat as she walks this way, and then she stops. Maybe a little more dramatic than she probably did. But the pushing of starting and the pushing of stopping, what starts her and stops her is also what starts the boat and stops the boat. And now you're beginning to see why looking at this as a system begins to make sense. Because if she gains some momentum this way, what do we know? The boat gains the same momentum that way, right? This has some momentum issues. Now, fortunately, we don't even have to calculate the momentum because they don't say how fast she walks. And surprisingly, it turns out it doesn't matter how fast she walks. If she walks slowly, that means she pushes with a little bit of force, and the boat is moving very slow, but for a long period of time. And if she pushes really hard, then she's going really fast, but for a short period of time. Either way, the boat ends up moving the same distance, as we will soon see here. So it doesn't matter whether she runs to Romeo or walks or crawls to Romeo. That distance that the boat moves is going to be the same amount. There's going to be a balance between the force and the time here. That's why we did momentum. That was this whole idea of this chapter, momentum. But this goes beyond the momentum. This goes to center of mass here. Because what have we been saying about center of mass? What was the neat thing about the center of mass? The center of the mass is what gave us a chance now to give size to our objects. And by giving them size, we can say that the whole rest of the pieces, and in this case, Romeo, Juliet, and the boat, if you put them together, isn't there some center of mass? And even though Juliet is pushing on the boat, the influence comes from the rest of the outside world. Is there anything pushing on them from the rest of the outside world? Isn't Juliet just pushing on the boat? And I think the whole reason they put it on the water is that things can move in the water pretty much frictionless. Not perfectly, but they can move back and forth. Whereas if this was on the ground, then there would be some friction there. And the whole idea here is to get you to think about this, that there would be some center of mass. I would suspect that the center of mass is a little bit towards the rear of the boat. Why? Yeah, the heavier object is near the rear of the boat. And probably the boat itself has more mass. If you've ever looked at a boat, you know, the bow and the stern look a little different here. So up here in the front of the boat, at the bow of the boat here, I don't know, it's kind of, I'm still guessing there's less weight there in the front of the boat than in the rear of the boat. But nonetheless, I'm going to say center of mass is maybe right about there. More towards the rear of the boat. I lifted it up a little bit too, because I would suspect that if they're standing or even sitting, they're above the bottom of the boat. So probably that is the position of the center of mass. And we won't need to know the vertical.
Is that changing?
Now, and there's my question for you. This is the center of mass before Juliet moves. What happens as she moves?
Changes.
Does it change?
The distance is changing.
And so this gives me a chance to say, didn't we learn this equation? Wasn't that Newton's second law? Now, granted, when we learned Newton's second law, didn't we apply it only to point objects? So now let me go a little bit further. Let me do this. Let me apply this to objects that have size. Okay? Now that my objects have size, I need to say this question. What forces are we talking about when we add up all these forces? It is the net force, but it's the forces that come outside of the object. If we had a point up, did we ever talk about what was going on inside the object? We never did. If I don't have a good point object, maybe as small as I can make might be this pin cap here. Before this chapter, when I tossed this across the room and I said it had a parabola, what forces gave it a parabola? What forces did we include? Gravity. Did we ever talk about the molecules and how the molecules bond together and the forces between them? We didn't, did we? We never talked about them. Now, maybe now that we're given our object size, we should at least mention them, and maybe we should call them inside forces, internal forces. How come we didn't talk about them? Why weren't they needed? How come they didn't matter? Were these forces just small? They were equal and opposites, right? If you have object 1 pushing on object 2, and that's back to this boat. You go to add up all the forces on this boat, doesn't, and when I say boat, I guess I mean boat, Juliet, and Romeo. But doesn't Juliet put a force this way on the boat? And then where's the force on Juliet? That way. If you put those two together, what's the total force? 0. And so the reason we never even bothered to even mention that there were other internal forces is because if we did, guess what the internal forces all come out to be? 0. And so we avoided it. And we can avoid it again, but now we're a little smarter. Now we know why we can't avoid it. But again, let's apply this equation to a bigger picture. An object that has size. All right, so when I go to add up all the forces on Romeo, Juliet, and the boat, taking that whole thing to be my object, all 3 of them, what is the total net force on all 3 of these guys? It's 0, isn't it? There's nothing pushing or pulling on this boat net. If you think about Juliet, I'll say it again. Juliet pushes that way. Is there a force this way on Juliet? Yes, but isn't there a force this way on the boat? And when you add the force on the boat together with the force on Juliet, what's the total? 0. Newton's third law. Those are equal and opposite. So any other forces would be like external stuff, like gravity. Well, do we have any gravity? Well, I guess we do. But of course, I claim that's being balanced by the buoyancy of the water. All right. So that comes out to be 0. I think the whole reason the author put it on the water is because then there's no friction to worry about. So there's no friction. The gravity and the buoyancy cancel off. Juliet's foot and the boat cancel off. Are there any forces here that are not going to come out to be zero? There aren't, are there? And that's the key to the problem. If you realize that all the forces add up to be zero, what would you say about the acceleration? It's equal to zero, right? And so wherever that center of mass is, it's saying it doesn't change. It doesn't accelerate. And so there's the key to the problem. And if you didn't see that, it's why I picked this one, because I think that's easy to miss. This is probably the hardest conceptual, the hardest physical one we've done this chapter, and maybe all semester so far, is because to even begin this problem, it's a lot like, number 5 we just did on the test. In order to begin number 5 on the test, you need to realize the speed cannot be zero. The normal force has to be zero. Then what does the speed have to come out to be? And in order to do this problem, you need to realize that all the outside forces, there really are none, and all the internal ones always cancel off because they'd be equal and opposite. And so wherever the center of mass is now, it will be later. Shall I draw it again after Juliet moves? I mean, what do you think this is going to look like? Yeah, I'm thinking it will look something like this, where the boat has moved closer to the shore by a distance d. But now Romeo and Juliet are very close together. And where's the center of mass? The same spot. Center of mass hasn't moved. Now, you might say, relative to the boat it's moved. Isn't the center of mass closer to the rear of the boat? I would put it the other way. I would say the rear of the boat moved closer to the center of mass than to say the center of mass moved to the rear of the boat. The center of mass did not move. That's the key to the problem. The boat moved, but not the center of mass. Okay? Now, if you don't, like I said, if you don't see that, you really don't know where to begin the problem. But once you do see that, it's a very easy problem. So, it's one of these magenta problems your author likes to put in there, because it's like, okay, it's hard to see it, but once you see it, it's easy. So, if the math isn't so difficult, it's all the other calculations here. So now let's try the calculations, because the question is, how far did the boat move? Yeah.
If the boat moves, but the center of mass doesn't move.
Yeah.
So what happens when the boat moves past that center of mass? Does it make a new one?
Can't.
Huh?
It couldn't move past that unless Juliet were to dive out the other end. I mean, it could look like this. It could look like boat and Romeo, center of mass here, and Juliet swimming along over there. Okay? And then I would get the same center of mass. But, yeah, so, it's okay. And then maybe this doesn't work anymore because now we have forces of water as she's paddling, and okay. But as long as she's in the boat here, there's no way she can walk far enough and quickly enough the boat moves there. She's always going to end up on this side of it. We got to get the center of the mass. Okay. But all right, well, let's talk about the numbers in just a second. That's a good question. Yeah.
So the center of mass will never change if there's no outside, if the outside force is zero?
Right, and that I want to make sure you hear, because we can't spend, well, we're already spending a lot of time here, but I can't overemphasize that enough. Why do I care about the center of mass? Because all the stuff that we did before is now going to be useful, even though our objects now have size. And we got to find that center of mass. And all the physics that we used through chapters 1 through 8, we're going to still use. And that's what I'm trying to convince you. If I had an object and I put it here and I said, the net force on that object is 0, what would you say about that object? It doesn't move, right? If the net force is 0, then I guess technically it means the acceleration is 0, which means it doesn't change its speed. But since its speed starts off at 0, that means it doesn't move. Fair enough? And that's what we would have done in chapter 5. No forces, no acceleration. If its speed is 0, it stays at 0. Fair enough? do the same thing here, except now I think it's a little harder to visualize because we have objects that have size and we have objects that move within that object. But I'm still really saying the same thing. I'm saying here I have a complicated object. It's got Romeo, it's got Juliet, it's got a boat. But if there's no forces, net force, there is a force from Juliet and the boat, I realize. But if their net force is 0, what does that say? The acceleration is 0. The acceleration of what part of the boat? Center of mass. So I'm not saying the boat doesn't move. I'm not saying Romeo doesn't move. I'm not saying Juliet doesn't move. They all move. But what I am saying is there's a magical point that doesn't move. What is that magical point? Center of mass. That's what this whole discussion here is about. Center of mass doesn't move. Other parts can move. You don't get that when you have just a single object. When you have a single object and you say it doesn't move, well then nothing moves. But when you have multiple parts, you can have one go this way and one go this way and still the center doesn't move. And that's what we have here. We have boat and Romeo going one way. We have Juliet going the other way. Together they don't move collectively at center of mass. And that's the key. That's the big step up between having no forces and nothing moves to having no forces and the center of mass doesn't move, but other parts can move. And that's why I wanted to make sure I did this one.
So if you had friction, then you can say the center mass will always the same, right?
Oh, right. Now, if I had friction, then this would come out to be a non-zero number, and then there would be an acceleration to the center of mass. And then I can find out what the acceleration is of the center of mass, and then I can find out where is the new position. And so let's say instead of being on water, this was in a very viscous fluid. So we're floating on maple syrup, you know, I don't know. All right? And so you're floating on this maple syrup. As you start walking, as Juliet starts walking, as the boat starts going this way, you would say that, hey, the boat is trying to go this way. I would think that that would apply a friction on the boat that way. Then I would have a number that way, and I would have an acceleration that way, and so the center of mass would probably migrate this way a little bit. Or put another way, the boat wouldn't have moved as far in the maple syrup as it would have in the water. Yeah.
Wouldn't you, the distance if you towards the shore, wouldn't that be the change in what the object center of mass, you know, is then?
No. Something like this. Here's the center of mass. If I were to move this object to here, and this object all the way to there, I still have no movement in my center of mass. So if the objects move, it doesn't necessarily mean the center of mass moves.
You just move one object in.
Well, if I move just one object, then yes, the center of mass would move.
But is that how you would find the distance, you know, close to the shore of the boat?
Oh, so let's go through it here. But I did want to make, and maybe I spent too long here, but like I said, unless you see the physical picture, unless you realize the center of mass is not going to move, you're kind of stuck on this problem. Once you realize that the net force is 0, which means the acceleration is 0, which means the center of mass doesn't move, you can then say center of mass before equals center of mass after. That is, before she walks, we have a certain position. After she walks, we have a certain position. That doesn't change. So now let's do a calculation. And of course, to do a calculation, I need an origin. I need to pick where do you want to call y or x equal to 0. So help me out. Where do you want to pick it? Where? Okay, I like where somebody said right where Juliet starts. Okay. And so I will take this position where Juliet starts, but I would emphasize you could pick it where Romeo starts. You could pick the center of the boat. You could pick 3/4 of the boat. You could pick the shoreline. You know, there's all kinds of things you can pick. And you're just going to come up with some, you know, variables. And like if you pick shoreline, you don't know how far the boat is from the shoreline. So you better call that a variable x, and then it'll cancel off. And you know, you just keep working with that. But I do know that the position of Juliet or Romeo is very important. So I'm going to call one of those 0. And somebody said Juliet first, so we have positive numbers. So I like that. And so here's how I would go ahead and do that. I would go ahead and say, all right. Let's calculate the center of mass. How do I calculate the center of mass? Well, I take the mass of the first object, which in this case is Juliet at 55, and her position is 0. Let me take the second object, which is Romeo. Romeo is 77. And maybe I need to give myself a little more room here. But what's Romeo's position? 2.7, right? So they clearly said Romeo is at the rear of the boat, 2.7 away from Juliet as he's doing the serenade. Okay. Then the next one is the boat itself. It's 80. Ooh. What's the position of the center of mass of that boat? Yeah, we weren't told anything about it. Now, if it was a symmetric boat, which is unlikely, we don't usually make symmetric boats. If it was a canoe, maybe I could argue that it would be in the center. But I don't think I can argue it's the center. It's at some position. So write it down. Maybe we'll figure it out later. Or maybe it'll cancel off. Don't ignore it. That's for sure. All right. So I'm going to say the position of the center of the boat, I don't know, is, should I use X? It's X. I don't know how far that is. I do suspect, though, by just knowing a little bit about boats, that it's more than halfway. Just because, you know, usually the back of that boat's got a few more seats, and it's got a squared off end versus a pointy bow in the front. So there's usually a little more weight towards the back of the boat. And purposely, you know, so you kind of have an angle up so you don't go nose down into the water. Okay. Okay. But I'm just going to say that's X. I don't know what it is. Of course, and then I got to divide by the total. So the total is 55 plus 77 plus 80. So that would be the way to calculate the position of it, which of course you can't literally calculate it because we don't know what the position or the center mass of the boat is. But I can do it on the other side. And so if I do it on the other side, I'm going to take again, here's Juliet. What is Juliet's position now? So did Juliet go all the way to 2.7? Why not? Because the boat moved forward, right? I mean, that's the whole point of the problem. The boat moved D this way, towards the shore.
So 2.7 minus D?
Yeah, so 2.7 minus D. I don't know what D is. I know. Write it down. There it is. I don't know what it is. But I know it's some number, so I know it's 2.7 minus D. And hopefully I'll find that D before the day's over here. That's the whole point, right? and now let's take the boat. I'm sorry, Romeo. Same order. Romeo. What's Romeo? And I think the whole phrase of plant a kiss on the cheek is to get them at the same spot there. So, okay, so Romeo and Juliet are in essentially the same spot there. 2.7 D. What's about the boat? What's the position of the
X minus D.
center of the boat? Right. So it was X, but now the boat's moved over by D. Right? And then, of course, divided by the sum of all of them. So fortunately, I don't really worry about the denominator. And for that matter, as you can see, this 80x that shows up there also shows up here. Then so this side reduces to 77 times 2.7. And this side becomes 55, 2.7 minus D. This side becomes 77, 2.7 minus D. And this just becomes a minus 80D. But one unknown, right? One equation, one unknown. Solve for D. We've got the answer. How far did the boat move towards the shore? Oh, and just looking at this stuff, I should have thought about this earlier. I don't know if anybody picked this up, but besides your test, there's a big wad here of papers, and then older papers that haven't been picked up, and I thought I'd send those around. You can also grab them in the lab in a few minutes, especially since we only have 10 minutes left here in class. But there would be my answer for D. Well, one more hard one, I suppose. What's the center mass of this? If I were to take this and lift it up, I need to find out how high its center of mass moves, right? So I'm not worried about how high did that corner move, right? I'm not worried about how high did this top move, right? What am I after? How high did its center of mass, right? If I toss it across the room, what goes in a parabola? Center of mass here. Now this one happens to be labeled here with a little colored dot there, but this is the center of mass. And you can kind of see it by spinning it. I mean, what if I were to put the nail right here and hold it? Right? You can kind of see that this behaves as if all the mass is over here somewhere, right? And if I were to put the nail right there, it would do that one. Fair enough? And if you were to put the nail right at the center of the mass, if you turn it, are you ever moving gravity off of its center of mass? No, right? And as you, of course, you spin it, it's not hopefully looking like fast, slower, something like this, right? It loses kinetic energy, gains potential, goes down, gains kinetic, loses potential. Because you would measure its energy by its center of mass. But here, right at its center of mass, it's not going up or down. So it just spins, right? And so again, this is the whole point of the second half of chapter 9. 9's a long chapter. So it's 10. 11 and 12 are really short, if that makes you feel any better here. But the longest two chapters of the semester are right here, 9 and 10. So how are you going to get the center of mass of this one? Now that we've done what I might call the simpler cases of the center of mass, how am I going to get the center of mass of this half circle? And so for our last example in this chapter here, let me draw a picture. And so here's my half circle. We'll call it radius R. Where's its center of mass? Well, maybe I will start with a little bit of guessing and then go just ask you this. Where do you want to put the origin? Where do you want to measure it from?
Origin? I mean,
Bottom left.
How about the center? I'm kind of liking right here at the center. And the reason for that is I'm going to do the easy calculation first. What is the center of mass in the x direction? Yeah, I picked it symmetrically purposely, even though it's not a square like we had done earlier. I'm hoping you can see that if you were to take this object and say, let's look at a chunk here and compare it with an identical chunk there. Forget the rest of them, but wouldn't you say that those two are the same distance and have the same mass? And so the center of mass of those two would be 0, right? And if you did it again with another chunk and an identically symmetric chunk, and maybe I should say column or stack here, where would the center of mass of these two be? 0. And so I think you can see how, from a symmetry argument here, that if I were to start to add all these things together, the center of mass is going to come out to be 0. So the center of mass is somewhere along here. And now you can probably see why I picked a half circle and not a whole circle. Because it was a whole circle, and I asked where is the center of mass in the y direction, what would you say? 0. But it's not a whole circle. It's a half a circle. So where's the center of mass in? Is it here? No. Do you think it's halfway up? More than halfway? Less than halfway? Yeah, I would expect it to be a little bit less than halfway, or maybe even a lot more than halfway. Probably not too much, but because of the tapering here, I would expect the center of mass up here to be much smaller than the center of mass down there. Fair enough? So how am I going to calculate it? Yeah, and I think you're beginning to see this. Again, I'll say it. This is one of the lessons of this whole semester. Could you write out the equation yourself? Never given it to you? Could you decide to do an integral or a derivative all on your own? And so I ask you again, what really is involved in an integral? It's a summation, right? And then what we have here, a summation? I mean, let's work it out here so that you can see it and practice by it, so that next August you'll be proficient on these, and I can just say, hey, good luck on chapter 23. Go and figure out the integrals yourself, right? Let's write this out here. But if I was doing this problem in the y direction, let me redraw it. I would draw it something like this. I would put my origin right there, and I would probably chop it into rows instead of columns, and saying, all right, let's add a bunch of these together. So the general principle, how much time we got? Ooh, this is going to be tough. Because I'm not going to show you any new calculus you haven't seen before. But I am going to apply a calculus in a way you've never done before. Watch. I'm going to say, let's look at the center of mass in the y direction. Now, according to what we've done, it would be the mass of the first object times the position of the first object divided by the total. Now, the total is not going to change, so I'm not going to focus too much about that. But we don't have point objects like we did before. And so what am I going to do? Well, I am going to call this little strip a certain mass. And so chop it into strips. And so this little m right here, summation, this is the mass here of a particular row times the position. Oh, and I should change that to a y. Sorry. And so that should be a y. But it's the mass of that row. Now, these are not well-defined rows. These are not cut out. So how do I do my calculus here? What am I really saying? Take the sum in the limits as what goes to 0?
The rows.
Delta.
Is it y going to 0 here?
Delta.
No, look closely at this. As this little strip gets thinner and thinner and thinner and thinner, this is y. Is y going to 0? No. What's going to 0? The mass of that little strip. And that is not what you've usually done in your math class. You've always taken position going to 0. But that's not what I want here. Okay? I don't want the position to go to 0. I want the mass to go to 0. And if you realize that, whoops, I already pulled that out in front, sorry. What would this become? Yeah, an integral. That's what I want you to see. Could you realize that I'm going to add an infinite number of pieces? And adding an infinite number of pieces is really a integral. And so what does the equation look like? Integral of what? It's dm, right? It's what did you take going to 0? Now remember, this is what's maybe a little different than you've done in any of your math classes. We're not doing anything, like I said, different in the sense that we're doing math. Just remember this, in your math class, when you took the limit as something went to 0, they meant it as a variable. They didn't mean it as position went to 0. They meant whatever the variable was. I know they always represented it as an x or a y, and you always are thinking x's and y's, but stop that. That's not what they meant by the variable x. What they meant by the variable x is a variable. It could be x as in space, but it could also be m as in mass. And so there is my integral. Okay? Now, I still got some more work to do. Right? What is my mass? Well, to answer that, I'm going to pull out this idea of density. Do you remember what density is? It's mass over volume. Can I just call it mass over area and kind of simplify it since we're looking at a two-dimensional picture here real quick? And so this would become 1 over the total integral of y. And if you think about this, think of this as a little bit of mass divided by a little bit of area. And so in place of mass, I will put density times a little bit of area. Oh, and I really should have saved just a few more minutes here. This is going to be a little fast. What would area be? Well, area would be the length of this little row times its thickness. And here's where my thickness would be called a dy. And so area then becomes L dy. What's L? Well, if I'm looking from here to here, and I call this x, then this is minus x because of the symmetry here, then I would say L is 2x dy. And that's the length of it. And then I would ask, how are x and y related? Well, isn't x squared plus y squared equal to r squared for a circle? So I can replace x with the square root of r squared minus y squared. So this integral becomes 1 over the total mass times the integral of y times rho times 2 times the square root of r squared minus y squared dy. And now I got exactly what I need. I've got my 2 and my rho pulled out in front. I've got my total mass. I've got an integral of y times the square root of r squared minus y squared dy. And I'm going to add up little strips starting here at y equals to 0 and go up until I get to my last little strip at y equal to r. And my final answer then, and I can even put density back as total mass divided by 1/2 of the area of a circle divided by total mass, integral 0 to r of y times the square root of r squared minus y squared dy. So, is the math harder? Yeah. Is the physics the same? Well, yeah. So I guess it's a little bit like question number 3 on the test. It's, look, just add up the forces and solve it. But if it's a differential equation, it's hard to solve. Here, if it's an integral, it might be kind of hard to solve, but that would give us the position, and I'll have to call it quits there, but that would be the position for a half circle. Now we would know everything about that half circle. We could calculate its kinetic energy, its potential energy, blah, 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 blah. So figuring out where its center of mass is very important.